We know it's a blue planet, and as humans, most of us are used to seeing the ocean from the safety of shore or glimpses of shallow waters. But did you know that the average depth of the ocean is 4,000 meters deep? This means that most of the world is actually deep sea. Yet we know so little about this mysterious and abundant environment. So as we experience rapid environmental changes above water from the climate crisis, so too is it affecting these extreme environments and the variety of amazing ecosystems within them. But not only is the deep sea affected by the changing climate, it's also a key player in mitigation by storing massive amounts of carbon in its sediments and by absorbing a huge amount of the atmospheric carbon dioxide and heat that we experience up here on land. It truly is the unsung climate hero of our planet. In today's episode, we'll learn about the key role the deep sea plays in regulating our climate, how scientists explore and study the incredible ecosystems and biodiversity within it, and how you can help protect these important ecosystems we know so little about. Hello, everyone, and thank you for joining us in episode 11 of the BMSC Climate Action Series. Today, we have a very exciting lineup as we dive down deep into the world of the deep ocean to explore some of the climate impacts, but then also how it's a major player in mitigating our climate. So we have our two guests joining us today, and our first guest is Dr. Kim Juniper, Chief Scientist with our partners at Ocean Networks Canada, which is a University of Victoria-based organization that operates cabled ocean observatories in the Pacific, Arctic, and Atlantic Oceans. He is also a professor in UVic School of Earth and Ocean Sciences and Department of Biology, and holder of the British Columbia Leadership Chair in Ocean Ecosystems and Global Change. He has authored more than 125 peer-reviewed publications on the microbiology, biogeochemistry, and ecology of deep-sea hydrothermal vents and other marine habitats. Kim also contributes scientific leadership and advisory roles to many national and international initiatives, including most recently the Canadian Healthy Oceans Research Network and the Partnership for Observation of the Global Ocean. In Canada, he's been a key player in the development, installation, and operation of cabled ocean observing networks since their humble beginnings in 1999 and 2000. Thanks so much for joining us, Kim. Please go ahead and start your presentation.
Thank you. Okay, I will go right ahead here, jump right into the deep sea. I've come up with kind of a comical title here because I think this is where we need to begin. I think most of us find ourselves in a position of these ladies here who know very little about the deep sea and for that particular reason don't particularly care about it. They've got more important things to worry about. So let's really start with the basics here. The deep sea really is the largest habitat on our planet. On planet Earth, dry land makes up about 25% of the surface of our globe. Ocean with less than 2 kilometers depth makes up another 11%. And then we have this huge 60% of the surface of our planet, which is covered by more than 2 kilometers of water. So that really works out to something in the order of 240 million square kilometers of seabed and 1 billion cubic kilometers of deep ocean water, most of which we don't know very much about. Our society has been making use of the deep sea in many different ways. One very important thing to remember before we begin is the deep sea really is an energy desert. There's no light down there, so no new food can be produced by photosynthesis. So the animals that live down there are essentially at the bottom of a garbage can, feeding on organic debris or carcasses that come down from the ocean surface. So as a result, they're really low abundances, they grow slowly, but we have an incredible high biodiversity that we're still trying to get a handle on. The estimates recently are somewhere between 500,000 and 10 million different species that are found in different parts of the deep sea. Our society has not really been making optimal use of deep sea resources. We primarily have in the past have been using the deep sea as the 240 million square kilometers as a dumping ground. We had a long period in the 20th century where we got rid of low and medium level radioactive waste and dumped it into designated dump sites in the deep sea. That practice stopped in the 1970s, but obviously that waste is still down there. At the end of the Second World War in particular, there were a lot of surplus munitions, both explosive and chemical weapons. And again, they were taken out to sea and dumped at designated sites on the seafloor. You can see if you look at ocean charts, there are still areas where there are marked ammunition dumps where you probably don't want to go diving or fishing. We still use that space to get rid of really large structures like drilling rigs and oil production platforms that are no longer functional. Rather than taking them apart on land, they tend to be taken out to sea and disposed of in international waters. We've also used that space in the deep sea to get rid of dredge spoils when we were dredging harbors and marine shipping lanes to keep them deep enough. We take sludge from sewage treatment plants and take them out to designated dump sites. Again, most of these practices have been discontinued, although we're still getting rid of dredge spoils in the deep sea. In the future, we're looking at using the deep sea volume and space for CO2 sequestration. In particular, there are two methods really. One is using both the volume of the deep sea water or the seabed, where we take CO2 that's been captured from the atmosphere or from smokestacks and disposing of it in liquid form in the deep sea. And then more recently, researchers have been looking at a more elaborate scheme where you have essentially floating air capture platforms like drilling platforms on the sea surface and a pipe that goes down below the seafloor to rocky outcrops underneath the seafloor where the CO2 is injected in liquid form and will actually turn into rock. So we're still looking at using the deep sea primarily as a dumping ground as we move forward. But as already mentioned here, the deep sea has also been our silent partner in slowing down climate change. The huge volume of water in the deep ocean has absorbed about 90% of the potential heat that could have gone into our atmosphere. If you look at this figure here, we can see how beginning in about the middle of the 1970s, we're essentially accumulating heat in the deep ocean. And about 25% of the fossil fuel CO2 that we've released into the atmosphere is actually dissolved in seawater, and much of it is now found in deep sea, in this 1 billion square cubic kilometers of seawater. We have been also exploiting deep sea fisheries, particularly on seamounts, these underwater volcanoes that come up closer to the sea surface. And that's where we find these slow growing, long-lived fish stocks, which are vulnerable to industrial exploitation because they take so long to come back. This is a graphic here that shows you the exploitation in terms of tonnage of deep sea fisheries. This is like the Orange Roughy fishery here. This huge trawl here is filled with fish from a seamount in the Pacific. As you can see, this fishery peaked about 1990, and then it's been declining ever since because, well, we're running out of fish. They take a long time to grow back. And we've moved on to the Indian and Pacific Ocean seamounts. And again, we can see we had a bit of a peak here and in the late 1990s, and now we're in decline there as well. So are we learning our lessons? Well, maybe. And then there are also the promise of genetic resources in the deep sea, of those 500,000 to 10 million of animal species and so far unquantified diversity of microbes. There's been a lot of talk about this as a potential source of genetic resources for biotechnologies and for drug discovery, for example. One example that's often shown here is this Yondelis, which is a anti-tumor agent, which was derived from this squishy looking organism here, a marine tunicate. It was developed by a Spanish-based company called PharmaMar, and it's clinically approved for treatment in over 57 countries for ovarian cancer. So that sounds very exciting, like a lot of promise. But the reality of this is that it takes a really long time and a lot of money to go from a collection of a sample in the ocean all the way through to a commercial drug. Somewhere in the order of 15 to 20 years from sample to market, and about $1 billion US to develop a single drug. And believe it or not, and despite all the hype that you may hear about drugs from the sea, 150 years of research have so far produced only 7 FDA approved drugs for marine organisms. So we're, I guess, at the beginning of the curve here, but let's not get too carried away with this possibility just yet. We're still exploring the deep sea. Researchers explore the deep sea from research vessels. We have all sorts of sampling and scanning equipment here. We see we're taking up a bite of the mud on the seafloor with this box core. These are other types of cores that are collected in the deep sea. You can see the orangey colored mud here. We collect water samples in the deep water. We send down various robotic vehicles from ships to scan and map the seafloor. And then if we want to go down to the bottom of the sea and explore some of the things, we use things like human-occupied submersibles. These were the first scientific submersibles used in the deep sea, where people actually get inside this vehicle, which is launched from a mothership at sea. And you can see this is the Alvin, which is an American-based submersible that's been operating since the 1970s. Essentially, the people are in a titanium sphere that's about 2 meters in diameter. And the rest of this is a battery case and thrusters for propulsion and a couple of mechanical arms that we can see here in the front of the sub, and then a basket to put samples in. And people go down to the seabed in one of these vehicles. In the morning after breakfast, we go down, we do our sampling and surveying for the day. Then we have to be back up at 5 o'clock in the evening for union-ruled supper time. And that's about all we have battery power for. As you can see, everyone here is wearing a toque because, well, he's not, but he should be, because there's no heat inside these vehicles. And most importantly, there's no bathroom either. Just in behind this gentleman here, there's a bleach bottle where everyone will turn their back if you have to stand up and make use of it. More recently, we moved from the adventure deep sea exploration in occupied submersibles to using remotely operated vehicles. These are robotic vehicles like this one here that's tethered to the ship. It goes down to the seafloor. It's operated by a pilot here who looks out through numerous cameras. And then the scientists sit comfortably back here in a row of chairs, watching what goes on and communicating with the pilot. The advantage of these vehicles, okay, it's not the same adventure going down to the bottom of the sea, but you can stay nice and warm here, and you can pop out to the bathroom or go to the cafeteria on the ship when you need to. If you need to bring in a specialist to help interpret something that you've discovered, well, you just go down the hall and find somebody and bring them into the dive. So in many ways, productively, it's a much better use of technology, but it's not as quite as much fun. At Ocean Networks Canada, we've taken yet another approach to exploring and observing the deep sea. We've installed these power and communication cables that go from land down to what we call node platforms on the seafloor, where we're able to get live real-time data from sensors on the seafloor. So this cable provides both power and two-way internet communication to a network of sensors that are on the seabed. And then users can access them online. So in terms of the deep ocean off Vancouver Island here's Victoria, Seattle, and Vancouver, just to situate everyone. And Ocean Networks Canada, we have a cabled observatory that's connected at Port Alberni at the top of this fjord here. And then we have an 840 kilometer loop of cable that comes out into the deep ocean and then back again. And our 3 deep sea sites, as we call them, are here at Barkley Canyon, a submarine canyon that we'll visit in a minute. Cascadia Basin, our deepest site here at 2,660 meters. And then the Endeavour hydrothermal vents that we'll learn more about when Ronki takes over. So this observatory here we essentially have, this is our node module. It's a huge structure here, sitting on the seafloor, sort of a pickup truck sized module that has the primary cable going into it, and then it's connected to these smaller instrument platforms in a kind of a network layout that we can see depicted here in the diagram. So how does this all work? Well, we have sensors on the seabed connected to a rather complicated informatics system here that manages the instruments, parses and calibrates data that comes in, detects events, archives the data, processes the data, and then makes them available to users through an online interface. Biologists can use this for a number of different things. First of all, we have rather unusually continuous, high frequency, long time series of data. We're taking many of the sensors, taking a measurement every second for up to 3 or 4 decades. So that allows us to, and then combining that with cameras, that allows us to really understand how organisms that we see here, their abundance varying over time, how they respond to different oceanographic events like temperature and salinity changes or changes in dissolved oxygen. And we can also set up experiments on the seafloor in front of these cameras and do real-time monitoring of some of these experiments. So here you see a camera platform that's monitoring these 3 little quadrats here, where we've injected an algal paste into the sediment to simulate an increase in plankton production on the surface that's forecast to happen with climate change. And we can also see seasonal effects. This is a migration of tanner crabs here that are going from deep water offshore. They're migrating up Barkley Canyon towards the coast. This is about 1,000 meters depth. And for 3 days, we saw this herd of tanner crabs passing here as they moved from the deep sea up to shallow water to actually mate and reproduce. So then the young ones then and the adults then move back down to the deep sea to feed and obviously avoid predators. So they take the risk to come up to shallow water for reproduction, but they go down deep where it's safer and there are fewer predators to spend much of their year. In addition to the fixed platforms that I was just describing, we also have in this same submarine canyon that we just visited, a mobile sensor platform by the name of Wally. Wally was originally deployed for the first time the summer that the Walt Disney film of the same name came out. So he got christened on the spot as soon as he was put down on the seafloor. As you can see, it's a tracked vehicle that has a whole bunch of sensors mounted to the front as well as cameras. And you can just see the tether here leaning up the back. So this tether goes back and loops around to one of our sensor platforms. So the operators of this vehicle who are based in Bremen, Germany, they get on to the internet and they can drive it around the seafloor here back and forth on their 70-meter leash and do put together photo mosaics of things like we see here. Every year, Wally is not brought back to the surface for servicing, but rather the doctor comes to Wally. So here we are coming down to do the annual servicing of Wally with the remotely operated vehicle, while the operators in Germany are bringing Wally around so that we can get up close to him. And the job today is to actually clean the camera dome here, which has built up a lot of scum over time. So we start with a basic toilet brush to get the bigger pieces off, and then we come in and do a little bit of detailing here with the suction sampler on the, and here we are, nice and bright and clean and ready for another year of photographs and video on the seafloor. In addition to these 3 deep sea sites, Ocean Networks Canada has another node near Bamfield at the Folger Passage Rockfish Conservation Area. So this is a buoy here that marks the underwater observing platform, and this is Folger Island. We're looking east here up the channel. At this site, we have essentially 2 platforms. This is our node here. Then out from the node at about 100 meters depth, there's an array of different instrument platforms. And then up on top of this rocky pinnacle at about 25 meters depth, we've got some other sensors here, as well as 2 video cameras, because this is the only place in our entire network where we have natural light that allows us to leave the camera on all day rather than having to use artificial light. And as I mentioned, this is a rockfish conservation area. There are a lot of rockfish around here. And this is not serviced by submersible, but we actually have commercial divers that come down with their little scrub brush here. As you can see them cleaning the sensors off, the end of the sensor head off of this current meter. Here's some of the data from that deeper site, just back up here a sec. We're now going to look at some data from this deep site here at Folger at 100 meters depth. And we're looking at actually a 12-year period that we've been recording continuously there. And we can just start to see some recent events that are rather interesting in terms of habitat and long-term ocean change. First of all, this first curve here shows dissolved oxygen at 100 meters depth over time. As you can see, it goes up and down over the seasons. Every year, it hits a peak in the winter, if you go down to January here, and then a low in the middle of the year, and then back up to a peak in and what's interesting is that salinity and temperature do the opposite. So what's going on here is in the summertime, when we have winds blowing from the north, we have an upwelling phenomena here off the coast, and that brings up cold, salty, but low oxygen water from offshore, brings it up to 100 meters depth here at the Folger site. So we have these low oxygen events every summer that are part of a natural cycle. Sometimes they dip a little lower than we would like to see them happening. But so far we have not had any serious events. And then also in between 2015 and 2017, you can see we had some really high summertime peaks in temperature over 12 degrees, which is warm for that part of the world. And this was part of this large marine heat wave called the blob that occurred between 2015 and 2017. And this was not a summertime heat wave as far as the ocean is concerned, but what really happened here is it was a failure of wintertime cooling, where we didn't get the big winter storms and cold temperatures that we have normally in the offshore area here. So the heat from the summer stayed, and then it built up over 2 years, and eventually we had peaks in heat here that are getting to the point where we're concerned about marine organisms. So looking ahead here, what are the threats to deep sea ecosystems? So I've touched on a few in terms of warming. No time to go into acidification today. Pollution, we've touched on a bit. Resource extraction, I mentioned fisheries, and I'm going to soon hand over to Moronki to tell us a little bit about her soon-to-be PhD project related to the extraction, deep sea mining. I'm just going to do a little bit of an introduction just to set this up. Ocean mining is on the horizon. We're looking at large mining vessels like this coming offshore with robotic vehicles that go down to the seafloor, scooping up minerals, and then pumping them back up to a surface vessel to eventually be transported to shore for refining. This is driven by economic growth. Let's just take copper as an example here. These are trends in copper consumption over time since the 1980s. Let's pay attention particularly to the Chinese consumption. So as you can see, as the Chinese economy grew over the decades, copper consumption really went up. You need copper to build new cities, to build new factories. Everyone needs copper for wiring. So this is driving a lot of this need for finding new minerals, and we are running out of copper mines on land. So there's a great interest in looking for minerals in the deep ocean. There are three types of what we call base metals, like copper and iron and zinc in the deep sea. There are the manganese nodules, which we'll talk about in a little bit. There are also cobalt-rich crusts, which are found on the slopes of seamounts. And then there are these polymetallic sulfide deposits. By polymetallic, I mean there's a whole bunch of different metals in here that are all glumped together in chimneys and large structures like this. This is what Moronki is going to be working on for her PhD. So this map here shows us where there are currently exploration licenses and known deposits of these types of metals. This light green area is a huge area of manganese nodules in the Central Pacific, of cobalt crusts on seamounts. The manganese nodules are these darker green ovals and circles. And the little red dots here mark the locations of these polymetallic sulfide deposits that we find on these volcanic ridges that are essentially go around the earth like seams on a baseball. These mineral deposits are also habitats for specialized deep sea organisms. The crusts are found on seamounts, and we get things like deep sea corals living on the seamounts right on top of the crusts. The manganese nodules have all sorts of little curious creatures on it, like this tiny little sponge here in the deep sea. And then the hydrothermal vents that form these seafloor massive sulfide deposits have an amazing array of extremophile animals and plants and microbes, pardon me, that can tolerate high temperatures and toxic conditions. It's really quite an incredible place. So the mining machines are really the new monsters of the deep. This gives you an idea of the scale of some of these robotic mining machines. This is one that was built for Nautilus Minerals for a project that eventually went bankrupt, but this was the first of these deep sea excavators that will be operated like this from a ship with a pilot sitting here with a joystick looking at all these screens down here and essentially mowing the lawn on the seafloor, collecting minerals. It's the scale of some of these mining operations that is of concern. If you look out here in the Central Pacific, this is the area of the manganese nodule provinces. And we can see that it's about the size of the continental US. And zooming in on this area here, which is in what we call the Clarion-Clipperton fracture zone between these two big fractures on the seafloor. These are all current lease areas and reserved areas for mining that belong to different countries who are under license to a UN agency called the International Seabed Authority. At this time, we're still in the exploration phase. So these different organizations here have 15-year renewable leases to explore and evaluate the economic potential of the manganese deposits. And then the next step, obviously, is to move on to exploitation. And maybe I'll just back up here for a second. A point here I wanted to make is that the size of these manganese nodule exploitations, in order to be economically viable, has to be somewhere between 10 and 100,000 square kilometers for each operation. Just to put this in perspective, Vancouver Island is sort of in the middle of this scale here at about 32,000 square kilometers. So this really would be a huge disturbance on the seafloor at depths of 5,000 or 6,000 meters in an environment where change happens very, very, very slowly. In fact, that's the reason that these manganese nodules form in the first place. The seafloor massive sulfide deposits that'll be a little different scale of operation. Most of these deposits are the size of a couple of football fields. So, but they're concentrated vertically. So one of these mining machines like we see here will be operated from a vessel, and they'll go down, essentially mow the lawn, chew their way through the deposit, crush the mineral material to a slurry, pump it up to the ship where it'll be screened and stockpiled, and eventually moved to shore for processing. Okay, I'm going to hand over to Maranke here. Stop my screen sharing, and certainly if there are questions, we will both be available to pick these up at the end.
Wonderful. Thank you so much for that great introduction, Kim. So many topics to explore. And of course, our next guest is Maranke Harris, who is an oceanography graduate student in the Juniper Lab at the University of Victoria. And she has recently returned to academia after working in industry on climate engineering and intergovernmental multi-vessel research expedition planning. She is fascinated with deep sea exploration, biogeochemistry, microbiology, and seafloor mapping. And Maranke's current research focuses on the implications of deep sea mining at hydrothermal sites through developing a microbial landscape model, which we'll hear a bit more about today. And beyond her research, she's also an avid science communicator and visual artist. So we'll link in the show notes where you can find out more about her work. Thanks so much for joining us, Maranke. I see you've started, so we're looking forward to hearing your presentation.
Thank you. So yes, I'm Maranke Harris, and I'll just start off with a little bit of who I am. So most of you by now from that lovely introduction know that I'm a graduate student within the Juniper Lab at the University of Victoria. I'm also originally from Toronto, Ontario, where I studied biological science at the University of Guelph. And here at UVic, I dedicate my time to deep sea oceanography, so life in the absence of sunlight. And my thesis is all about hydrothermal vents thousands of meters below the ocean's surface, where I focus on the mineral and microbial resources of the deep sea. So on top of getting to study these extremely fascinating remote locations, Kim and I also get the opportunity to communicate our science with you and what we find fascinating with viewers like you all. So with that, let's jump into the science. In 1997, the discovery of deep sea hydrothermal vents altered the global perspective concerning the boundaries of biological systems. So thousands of meters below the ocean surface in complete darkness, where the familiar process of photosynthesis couldn't possibly occur, dense communities of animal species were found not only existing, but thriving. So the extreme environments of hydrothermal vents redefined the maximum temperature limits for life on Earth and provided novel resources for medicine and technology advancements. So I'm sure the first question on some of your minds might be just what is a hydrothermal vent? A hydrothermal vent is a crack on the seafloor from which superheated water warmed by lava at the center of the Earth discharges. So temperatures of the water coming out of these vents can reach as high as 400 degrees Celsius. And here's an example measurement from a few years back that got up to 324 degrees Celsius. So hydrothermal vents are found within the deep ocean, thousands of meters below the ocean surface, anywhere from 1,000 to 4,000 meters down, and they exist in complete darkness. As I mentioned on my last slide, they were discovered in 1977, so they're a fairly new branch of ocean science. Humans have been exploring the ocean for centuries, but hydrothermal vents only became known to us about 40 to 45 years ago. Because of the remote location and the lack of sunlight, scientists long assumed that the bottom of the ocean was a barren place. But the discovery of hydrothermal vents changed all of this. So what you're seeing on the screen is an example of some of the life that exists down there. These are tube worms, and they're able to survive because of tiny bacteria found in their cells, which take the chemicals coming out of the vents and turn those chemicals into energy. And this is a process called chemosynthesis. So I'm sure you've all heard of photosynthesis. Photosynthesis and chemosynthesis are both processes by which living things produce food, but the key difference is that photosynthesis is powered by sunlight, while chemosynthesis runs on chemical energy. So at hydrothermal vents, this energy comes out of chemicals in the chimney of the vent and also chemicals in the superheated water that is being pushed out of the vent itself. As I mentioned earlier, the resources of the deep sea my thesis involve are mineral and microbial. So concerning minerals, largely base metals, so things like copper, iron, zinc, and lead, these largely base metal mineral deposits precipitate from hydrothermal fluid as it interacts with the cooler surrounding seawater at or beneath the seafloor. And they're mainly located within mid-ocean ridges where tectonic plates diverge. So about 65% of all of these SMS deposits are at these mid-ocean ridges. And globally, we estimate a 600 million ton resource worldwide. Part of studying these deposits involves mapping or modeling their location and size, which requires visualization. So there are plenty of ways scientists and marine professionals visualize the deep sea. Pertaining to my research, the methods are mainly split into two main categories: bathymetry, which involves audio cues used to create maps, and photogrammetry, which uses visual footage to create models. I'll begin with bathymetry. So in order to understand bathymetry, one needs to understand the behavior of sound within water. Sound travels faster within water than it does within air. The typical speed of sound within air under typical conditions is about 343 meters per second. In comparison, sound travels at around 1,500 meters per second through water. And multiple things within the ocean create sound, and this sound is emitted from the source in all directions as a series of spherical pressure waves. So using this principle, how do scientists know what the seafloor looks like? Because sound waves travel through the water at a known speed, once scientists know the travel time of the wave being emitted from the source, here the source is a ship, they can then calculate the distance to the ocean floor, or in this case of the image being shown, a torpedo. So they can then combine all of these distances to make a map of the ocean floor. Therefore, bathymetric techniques utilize sonar to detect the ocean floor. And sonar, or sound navigation and ranging, is a technique that is used to that uses sound propagation to navigate, measure distances, and communicate with or detect objects under the surface of the water. There are two main types of bathymetry, multi-beam and single beam. Multi-beam bathymetry uses high resolution, and it uses a number of sound pulses from a mounted system, which is shown here as mounted on the hull of a ship that covers a fan on either side of the vessel across the track. It's kind of like taking a broom and sweeping across the seafloor. So the swath is typically about 5 times the water depth. Therefore, shallow water will have more narrow swaths than deep water. And the image in the center and the image to the right of the screen show an example product of multi-beam bathymetry. So as the survey ship moves, each set of pings adds a series of depth along the track, and successive sound pulses build up data along that track of observation. The type of bathymetry I work with uses sonar mounted to the hulls of ships, as seen on the previous slide, but also sonar mounted to AUVs, or automatic underwater vehicles. So AUVs hover about 20 to 90 meters above the seafloor, whereas ships, if everything is going well, are located at the surface of the ocean. So AUV bathymetry gets a closer look than ships and is higher resolution, therefore. Single beam bathymetry can be hull mounted or AUV mounted, just like the multi-beam bathymetry, but the main difference is in the swath of the beam that it emits. It uses a much more narrow sound pulse from the mounted system, shown again as mounted from the hull of a ship to the left of your screen. So if multi-beam bathymetry is like taking a broom and sweeping across the seafloor, single beam bathymetry is like taking a bristle of that broom and dragging it across the seafloor. It's a much more narrow field of view. Here's how bathymetry is incorporated into my research at the University of Victoria. Here you're seeing the Magic Mountain Bent Field on the Southern Explorer Ridge. It's about 130 nautical miles off the west coast of Vancouver Island, BC, and depths go down to about 1,850 meters. And what's cool about this area is it's only been visited twice, so once in 1984 and once in 2002. On the right of the screen, you're seeing its general location, and then to the left, you're seeing a map of the bathymetry showcasing a combination of pencil beam and multi-beam bathymetry. So note the resolution differences that I mentioned earlier. There's a much larger, less detailed area surrounding a smaller, more detailed area, and the less detailed area uses hull-mounted bathymetry, whereas further from the seafloor, whereas the more detailed area is using that AUV-mounted bathymetry closer to the seafloor. The second method that I use to visualize the seafloor is photogrammetry, which uses visual footage like that captured by the camera on a remote operated vehicle or ROV to create 3D models like the shipwreck that you see on the left. Photogrammetry is completed using videos and images. So the method that I use takes ROV video footage of hydrothermal vents and splices it into thousands of photos. Then those photos are stitched together in modeling software to create our 3D model. Here's how photogrammetry is incorporated into my research. So this is ROV video footage of the Endeavour hydrothermal events that Kim mentioned earlier. This is focusing on the Dante edifice specifically. So as you can see in the video to the left, video is taken with the ROV in vertical transects. This is a sped up ascending transect. They go much slower than this to be able to capture all the detail. And this means that the ROV starts at the bottom of the edifice, videotapes in a straight line all the way up to the top, moves about 1 meter to the left, and then videotapes in a straight line all the way to the bottom, moves about 1 meter to the left, and continues that process all the way around the edifice. And that video is then turned into our model. So the video here on the left shows the 3D model of the Dante hydrothermal vent edifice. You can move it in 3D space and get a closer look. It's pretty detailed. And the model is a result of 3,200 images stitched together. So it takes about 52 hours of processing to create, and that's 52 hours per attempt. So that's just 52 hours if you get it right the first time. So if you don't get it quite right, as you could probably tell, I didn't on my first try, you have to go back, and you can imagine how the hours add up. But it's fun and worth it in the end. So now that you know how we visualize the seafloor and those SMS sulfide deposits, but as you know, the resources of the deep sea are more than just mineral. So you might be wondering where the microbes fit in. Microbes are a large, diverse genetic reservoir with largely unexplored medical and commercial potential. One use that we know of stems from antibiotics that are isolated from secondary metabolites in deep sea sediment microbes that counteract the spread of multi-drug resistant bacteria. So the bacteria that I'm interested in are located within microbial mats on the seafloor and within tube worms themselves, because as you'll remember from earlier in my presentation, tube worms don't have a mouth or digestive tract. They survive based off the chemosynthesis that's created by the bacteria found within their cells that they work together with through symbiosis. So we collect visual information to map these habitats, and then we collect microbial samples to learn about the microbiology of these habitats. And then we take our microbiology data and our map and merge the two to come up with an assessment of the bioprospecting potential of the deposit. Later this year, we're going to be doing some microbial sampling in collaboration with Schmidt Ocean Institute at the Mid-Atlantic Ridge. This will involve researchers from all over North America and Europe. And by examining the genetic properties, we'll be able to add a microbial layer to those maps and models that I showed you earlier. So vents have a life cycle. They start out actively spewing that superheated water like you saw in some of the first videos I showed you. And then over time, venting slows until it eventually stops and the vents and chimneys begin to erode away by weathering from the water surrounding them. So this sampling will involve characterizing microbial communities at various vent life cycle stages to determine how composition of metabolic features of the microbial community shift along with the aging of those sulfide deposits. And that's particularly important because inactive sulfide deposits are first up for mining right now. They're being promoted as a way of avoiding damage to the equipment that would have come from the high temperatures found at active venting sites and the endemic biomass of fauna that we know exist at active vents as well. So if you're interested in learning more about a day in the life on a research vessel, I'll direct you to the Nautilus Live Instagram page, where I got the opportunity to document my experience as an ocean science intern aboard Nautilus last August. And it's saved in their highlights. There are also many more perspectives from all kinds of individuals who have had the opportunity to sail aboard Nautilus. So I was an ocean science intern, but you can look into day in the lives of mapping interns, science communication fellows, other people who work with the Nautilus as well, other employees of Nautilus Live and the Ocean Exploration Trust. The last thing I'll leave you with here is, although SMS deposits host resources that are comparable with what's found on land, they do differ in some ways. So the land-based deposits are highly clustered and they have a much larger median size than the sea-based deposits. The sea-based deposits are largely spaced out and have that much smaller median size. So as it currently stands, SMS mining is what we like to call boutique mining, and destroying the rich microbial diversity for the supply of metals is likely not worth it. And this is why both resource potentials need to be considered. Thank you for listening. And if you're interested in hearing more, you can find my platforms on social media on my science communication Linktree website at Imaginative Sci.
Thank you so much, Maronke. That was a great presentation. Wow. I think that we've explored not only what's in the deep sea, how it's impacted by climate change, but also how scientists study the deep sea, which, as you mentioned, is a relatively recent field. So if anyone has questions, please go ahead and put them in the Q&A function. To start us off, Kim, I have a question. You mentioned briefly there's some recent interest in carbon capture and capturing that carbon and injecting it into the deep sea. What are some of the side effects of that process?
If we look at carbon capture and direct injection into rocks beneath the seafloor, then environmentally, we're still at the beginning. We're assuming that it's not going to affect any known ecosystems. However, we do know that there are microbial ecosystems within the seabed itself. Below the seafloor, it's not solid rock. They're particularly near the mid-ocean ridges. There's a lot of open space there, which is the reason why we have room to inject a liquid CO2. There are microbes that live there. They make their living by growing very slowly. There's no new food coming in, so you're primarily limited to gnawing away at the rock. And I think if we look at the scale of these proposed injection sites and the scale of these, what we call the deep biosphere, the microbes that live within the seabed, I don't think we're worried at this point, but it is certainly something that's going to require more research because there has not been a lot of exploration of the microbiology of below the seabed itself. You need to drill into the seabed, and these are very expensive operations.
Interesting. Thank you. That's not something that we usually think of, especially with the sort of macro fauna you showed of the worms at the hydrothermal vents. And Maranke, you mentioned that you're mapping microbial mats on hydrothermal vents. I was wondering if you could comment on the actual process of gathering microbe samples. How does that actually work in terms of, the drastic change of light, temperature, pressure that they experience moving from the bottom of the ocean to a research vessel, or even over time due to the effects of climate change, how that might be affecting them?
Sure. So in terms of gathering microbial samples, for microbial mats, what we do is we use the suction sampler on remote operated vehicles. So it's basically just like a little well, it's not too little, but it's a vacuum arm that'll just suck that mat right up off of the seafloor and put it in the storage chamber to be brought back up to the ship itself. And then once we get those samples back on the ship, we start processing them. So what we do is we just freeze them at around minus 80 degrees Celsius for later processing in the lab. So we just want to preserve them as they are until we can deal with them. Because if you were to not freeze them, then you would have the issue where they would start changing before we could actually work with them and keep their genetics as they are at the bottom of the ocean.
Thank you for that. Kim, we have a question kind of coming back to, you mentioned that the deep sea sediments have played a really big role in sequestering carbon. And we have a question from an audience member who's asking, is there a concern that mobilizing deep sea sediments from mining could release that carbon that they've sequestered?
I would say that the biggest concern at this time is not so much mobilizing the sediments will be brought back to the surface and then probably released at depth once we've removed all of the minerals from them. So that is less of an issue than the fact that we're bringing up probably millions of cubic meters of seawater from the deep, depressurizing it as it comes to the surface. So dissolved gases in that seawater are naturally going to be released to the atmosphere on board the ship during the sieving process. And we just need to sit down and work out the numbers in terms of, does this really represent an important re-injection of CO2 back into the atmosphere as we depressurize these compressed gases?
Right. That would almost be working backwards from what's been happening in the sea as a climate buffer for the last 100 years.
Exactly.
Okay.
I just wanted to add one thing that, there was a time when deep sea mining, we had a romantic vision of it back in the 60s and 70s, a bit like right now we see asteroid mining. This is something, a faraway resource that's going to solve all of our problems here on Earth. But when you get a little bit closer to actually doing it and learning more about the environment where the exploitation is going to happen, you start to realize that there is no real free lunch.
Not how it goes. You mentioned that the International Seabed Authority is the regulating body for those leases that you showed, that massive area of exploration and potential exploitation. What is Canada's role in the ISA, or in just that sort of like regulatory framework? Where is that at?
So right now, the International Seabed Authority is in the process of finalizing the draft regulations for deep sea mining. So this has been a process that's been going on since, well, I would say the last 7 or 8 years. The ISA works a bit like the UN General Assembly, and in fact, they use the same terminologies. They have a Secretary General. They have the headquarters in Kingston, Jamaica. And then once a year, they have an assembly of members, all the countries that have signed on to the United Nations Commission on the Law of the Sea, turn up once a year for their annual meetings to vote on issues. And then they also have what's called the Legal and Technical Commission that really addresses some of the technicalities, deals directly with the mining companies. So right now we're in a bit of a sped up process to try and finalize the mining regulations so that the leaseholders can then proceed to actually extracting mineral resources if that proves economically viable for them. So that's expected to happen sometime before 2024.
Will there be some sort of feedback or process to give feedback on that draft?
There have been multiple feedback steps. There are a lot of researchers like myself who've been involved in reviewing draft regulations, commenting on them, as well the individual member countries of the authority, their representatives comment on them. These are debated in chamber. And so, yeah, it's been a long back and forth process. I think we're at the 7th version of the draft regulations right now.
Moronki, we have a question about the mapping of the hydrothermal vents that you're working on from Maynard, who, if people remember, was one of our guests in episode 3 of Science Communication. Welcome. He's asking, what do you see as some of the most useful applications of what we're discovering at the hydrothermal vents?
Hi, Maynard. Nice to hear from you. So pertaining to my research specifically, the most useful application would be what my whole thesis surrounds. So mapping and modeling those habitats to determine where microbes are situated on these edifices so that we can quantify bioprospecting potential. And the reason why we're doing that is because if you're examining resource potentials of the deep sea and hydrothermal vent and sulfide deposits in particular, when you're looking at the detriments of mining and trying to combat that, mining is a much more invasive resource extraction process. When edifices are mined, you'll basically lose all of the ecosystem and biodiversity down there, which is why we're advocating for consideration of the biodiversity of the microbes that are vastly understudied. Because if we were to destroy these ecosystems without thinking about the potential that they could provide us with a more renewable resource, like the microbes will regenerate faster than those sulfide deposits will, definitely. So if we don't think about other resources that are more renewable and we just rush to the quick money and destroy the mineral resources and in turn destroy the ecosystems, then we're missing out on potential for ourselves. From a more self-centered point of view, we're destroying the ecosystem, but then we're also hindering our own human advancements.
Right, absolutely. Thank you for that. Kim, I wanted to come back to the graphs that you showed when you were showing the temperature peaks and oxygen dips that corresponded with that from the cabled observatory data. Is there a point where the deep sea can no longer absorb heat or carbon at the rate that it has been to help regulate our climate? And is there sort of a concern with those anoxic areas?
Okay, let's just first situate the data that I showed you. That was from 100 meters depth, just off Bamfield. So this is an area that's subject to much stronger what we call seasonal changes in temperature and dissolved oxygen than the actual deep sea itself. When you get down to 2,000 meters and deeper, it's pretty dull. Temperature changes are measured at hundredths of degrees. Dissolved oxygen, there's not a huge amount of consumption either, because there's not a lot of decomposition going on. So much of that worry is really something that occurs in the coastal zone. In terms of the capacity of the deep sea to absorb heat from the atmosphere, that depends on a lot of different things, particularly as, if ocean circulation changes drastically because of climate change, that may and will affect the capacity of the ocean to absorb heat from the atmosphere.
Will that slow down?
Well, it depends on which way we go. Much of the atmospheric heat is absorbed in areas where we are actually have vertical circulation in the ocean, so that the warmer waters on the surface will actually find themselves pushed down deeper because of physical interactions. So if you think that the exchange of heat between the atmosphere and the ocean really depends on the difference in temperature. The smaller the difference in temperature, the warmer the ocean, and the closer it gets to atmospheric temperature, the less heat you're going to have exchanged going back and forth. It's a bit like trying to chill a bottle of wine. If you put it in lukewarm water or you put it in really cold water, that's obviously going to suck the heat out of the wine a lot more quickly than room temperature water.
Yep. So the oceans are wine bottle, okay? Or we're the wine bottle.
Yeah, but I wouldn't recommend drinking.
Right. Okay. Now, you've been in one of those submersibles that you showed a photo of, right?
Yes.
That's really cool. I have a very basic question for you. How cold is the bottom of the sea?
Much of the deep sea is somewhere around 2 degrees Celsius once we get down to a certain depth. So if you imagine yourself going down to the seafloor for the day in a vehicle like an inhabited submersible, it cools down as the day progresses, because you can't really afford to use battery power for heating. So you dress warmly, put on a toque and long underwear and a couple of pairs of socks and warm woolies, and you get through it. You don't stay long enough to go hypothermic or anything, simply because most submersible operators require the vehicle to be back on the surface well before dark, because if there's an emergency, it's really difficult to recover in the dark.
Right. Thank you. And one last question for both of you. Just being mindful of time here. This is a relatively recent avenue of research. So I'm curious where you think more research should be prioritized when it comes to the deep sea and the intersect with climate change. Maranke, I'll ask you to go first for this one.
Sure. The first thing that came to mind once again is just my own research. I guess that's where my mind's been recently. So basically just promotion of consideration of microbes within deep sea environmental impact assessments. Because at the moment, they're vastly understudied. We don't know as much about them as we should, particularly pertaining to how they change along the vent life cycle. So as I mentioned earlier in my presentation, those inactive vents are vastly understudied. And even the active vents, we don't know enough about the potential that lies there with the microbes and the genetics themselves.
Thank you. And Kim?
Well, I think I would go for pushing a better understanding. As I mentioned, we have all sorts of ideas of using the space in the deep sea to help mitigate climate change, particularly CO2 injection and sequestration. And we need to know more about this before we start doing it. And particularly the long-term environmental effects. As you saw for decades, almost a century, we used the deep sea bed as a dumping ground because we didn't think it mattered. And now we're moving on to using it for CO2 sequestration, particularly going below the seabed because, well, we don't know much about it, so why should we care? And so I think we need to dig into that a little bit more so that we can do this in an informed and hopefully sustainable way.
Thank you both so much. Wonderful presentations today, and great to be in conversation with you about this deep topic. And so we'll end today with our usual climate action recommendations. Not many of us have a chance to go to the deep sea. We saw some amazing videos today. And so one of the resources we are going to hand over to you, as Kim mentioned, there are cameras at some of the cabled observatories. And Ocean Networks Canada has an incredible YouTube channel where you can go and see some of the best videos of little deep sea creatures that are little or big, deep sea creatures that are down there. So it's just a chance for you to actually see like, wow, there is life at the bottom of the ocean. So you can do it from the comfort of your living room where there's a bathroom nearby and you don't have to dress warmly all day. The second sort of theme that's come up today is this tension between thinking we need these deep sea minerals and resources to transition away from fossil fuels, while also being mindful that we don't know what the impacts could be of deep sea mining, either to the habitat or in that process, as Kim mentioned. And so one of the things we want to keep in mind is that how can we actually recycle a lot of the minerals that are in our electronic products that we might not be using anymore? So there's more and more attention to this. And so we'll link to some resources where you can learn more about it. There's also two organizations, the Deep Sea Conservation Coalition and the Deep Ocean Stewardship Initiative, and they have more resources on their website. So we'll direct you towards there to find out more. And finally, we know that deep sea research is still relatively recent and so much is yet to be learned about carbon sequestration, carbon injection, or even carbon cycling for a healthy future and a healthy climate. And so we'll link to some of our favorite reads on this topic so far, so you can also learn more about these topics. And we'll be sure to link to Moronke and Kim's research pages or science communication. So if you have more questions, you can ask them too. And our next BCAS episode is just a few weeks away on Wednesday, March 9th. We're going to go into the topics of climate education and misinformation, which, as we know, is a theme that covers many topics besides climate. And so we hope to see you then. And we'll end today with our ocean-themed joke. Where is the deepest part of the ocean? It's at the bottom. It's where the deepest part is. Yeah. You're welcome. Anyway, thanks for joining us this week, folks, and we'll see you next time.